Right. Thanks for coming. It's very exciting to give the very last talk of the conference. So today I'm going to talk about my joint work with Haar, which is approximate unitary T-designs using short random quantum circuits with nearest neighbor and long-range gates. Okay. So let's just start off by the main question that this talk is focused on. So basically the question is, how fast do random quantum circuits converge to the uniform measure? So the organization of this talk is according to the elements and the objective of this question. So I'm first going to define what do I mean by the uniform measure, and then I'm going to define the random circuit model, and then I'm going to explain what it means to converge to the Haar measure, so what measure of convergence we're interested in. And then I'm going to talk about the results and the proofs and definitions. All right. Sorry. Okay, so the uniform measure. So the ideal mathematical definition of the uniform distribution over a group is according to the Haar measure. Which essentially is what we mean by uniform. And the definition is that the distribution has the property that if I sample an element from it, and if I translate it by an arbitrary unitary element, let's say if you're talking about the unitary group, then the sample is going to be again according to the Haar measure. So basically the distribution is invariant under translation by arbitrary elements of the group. So pictorially, this is like basically a gigantic unitary group, and I want to just sample a random element. Oh. Okay, so the Haar measure is known to have extremal properties. For example, they're known to generate a large amount of entanglements, or they can be used for a lot of protocols in quantum information, like randomized benchmarking and so on. So I'm going to talk about three particular applications that is going to be related to this talk. So the first one is the scrambling, that basically random Haar unitaries scramble fast. In the sense that if I start, let's say from the all zeros state and apply a sample, a unitary sample from the Haar measure, and then look at a small enough subsystem of the subsystem, then it's essentially close to the maximally mixed. So basically, the local parts of the system don't have any information about the global the global state. Or the property can be related to operational tasks. So for example, decoupling. Oops, sorry. This is very confusing. So for example, decoupling. That basically the Haar unitaries are known to be able to decouple correlations between the parts of quantum systems. For example, consider an experiment that I start with a maximally entangled state, and I prepare a large, relatively large pure state here. And if I apply a uniform Haar unitary between this pure state and this right-hand side of the entangled state, then the left-hand side is going to be decoupled from any small enough part of the qubits. So basically, the density matrix corresponding to M and S is going to. I'm sorry, what's going on? Okay. So it's going to be decoupled. Right? Another property that we can think of about the Haar measure is basically the concentration properties of the output distribution of the unitary, let's say in the computational basis. So again, consider a simple experiment that I prepare all zeros states and apply a Haar random unitary and sample a string, a string of bits. And I'm interested to see the probability distribution that is coming from this unitary. Is it concentrated or not? So we can quantify concentration according to this so-called collision probability that is defined according to the following. Suppose that I apply sample two independent strings, x and y, from the output of U. And the collision probability is going to be the probability that these two strings are equal to each other. So if your distribution is very concentrated, then with high probability, these two strings are going to be like the same strings. And if it is not concentrated, they are not going to be the same. So for example, if like you apply the identity unitary, so basically the output distribution is fully concentrated. It's just going to output all zeros a state, all zeros a string. And the collision probability is going to be just 1, so it's going to be large. And if your unitary is n-fold tensor product of Hadamard's, let's say, then the collision probability is going to be small, 1/2 to the n. So here's the definition. So basically, it's the probability of two strings colliding. And in terms of the unitary, I can think of it as sum over all bit strings, the amplitude of starting, the absolute amplitude of starting from 0 and obtaining x to the power 4. So here is an example. Here is a way to explain this. So if you have a uniform distribution, like in general a uniform distribution over all bit strings, then the collision probability is going to be 1/2 to the n. And if it is fully deterministic and concentrated, then it is going to be 1. So now the question is, where does the Haar measure sit in this spectrum? So as I go from left to right, the distribution is going to be more and more concentrated. And so what happens is that we expect the Haar measure to output distributions that have collision probability that are essentially close to uniform. But so that means that they're not concentrated, but they are also far from uniform. So something like constant over 2 to the n, like as compared to 1/2 to the n. All right, so now now having all of these interesting properties from the Haar measure, the question is, how can we generate them in experiments? Or like, is Haar measure a realistic measure of randomness? So what turns out is that so each element of the unitary over n qubits has exponentially many terms. So inevitably, you need exponentially many random bits and random gates to generate them. You can generate an element of the Haar measure using, let's say, a random circuit with exponential depth. But there is exponentially many gates there, so this is not something that we can actually see in nature. And so if you look at this picture, so basically the random circuit model, that is basically the application of random gates between qubits, is going to be like something in like a Brownian motion on the space of unitaries. And as I run the random circuit more and more, I'm going to explore the space, and I'm going to converge to the uniform measure over the unitary group. But if I constrain my circuit to have only polynomial depth, then the distribution that is resulted by a polynomial depth circuit does not have enough support in order to generate any element in the unitary group. So the distribution is essentially going to be very different from the Haar measure. So now the question is, what can we say about the distribution generated by a random circuit? And by construction, it is an efficient distribution, so it would be great to understand what we get. So having said that, given this explanation, let me revise the main question that I started off with at the beginning of the talk. So basically, the question becomes, how fast do random quantum circuits converge to the uniform in weak but practical or useful measures? So we know that they can't converge in the strongest possible measure, but now the question is, what measures are realistic, and how fast does it take until I converge according to those measures? Okay, so now I'm going to explain what I mean by the random circuit model in more details. So I'm going to focus on a particular configuration of qubits. For example, so I'm going to in particular talk about configuration of qubits on lattices or a complete graph. So for example, a lattice of dimension 1 or a chain is a chain of qubits, and When I say apply a random circuit according to this architecture, I mean that at each time I'm only allowed to apply gates according to the edges of this graph. Or a two-dimensional lattice the same way, and so on. So D is the parameter that defines the dimensionality of the lattice. And the diameter corresponding to to each of these graphs is going to be n to the power 1 over d, where n is the number of qubits. Or I can, and I'm going to also talk about complete graphs, where basically I'm allowed to pick any pair of qubits and apply gates between them. Okay, so for example, the one-dimensional architecture is going to be the application of, let's say, 2 qubit gates between nearest neighbor qubits. And so the number of layers is going to be the depth of the circuit, and the size is the total number of gates that I have. Or I can think of the two-dimensional grid that, like, I locate the qubits on a two-dimensional lattice, and I can apply gates, let's say, in parallel between pairs of qubits on the rows. Or like in this way, so there are 2 ways to apply qubits on the rows or on the columns. And a random circuit, according to the 2D architecture, is going to be a combination of each of these ways of applying the gates. And for the complete graph, as I said, it's going to be that I can apply gates between any pair of qubits, so I can pick any pair of qubits and apply gates between them. Okay, so now what do I mean by convergence? So let's think about the landscape of hardness, the landscape of randomness that is generated by a random circuit model. So this is the depth of a circuit that I apply. So I haven't specified the circuit architecture. And so it's going to be just the conceptual way of explaining what I mean by the measures. So at depth equals 1, basically I haven't applied any gates yet. So the unitary is just going to be the identity. And we know that after exponential depth, the unitary is going to be very close to the Haar. So for example, consider the entanglement between parts of the system. So consider the experiment that I implement a random unitary on the n qubits that are initialized by all zeros a state. So if I apply a fully random unitary, then I'm going to be in maximal amount of entanglement. So here's the diagram. This is the entanglement between the parts of the system. Now consider the random circuit model. At the beginning, the distribution, the amount of entanglement is just going to be 0. And as I continue applying gates, I'm going to increase the amount of entanglement. Now, suppose that the situation is such that after a short amount of time, I'm going to get very close to the maximal amounts that I can achieve. Then basically, it's just enough to run the circuit for this much. And that would basically give me the convergence that I need, according to the application here just being entanglement. So here, entanglement defines a measure that I'm measuring convergence of the random circuit based on. So also we can talk about a variety of applications. For example, we can have scrambling or decoupling that I explained at the beginning of the talk, or the concentration property, basically having anti-concentration output distribution from random circuits, or entanglements, or like quantities like out-of-time order correlators that are related to condensed matter physics or high-energy physics. So each of these applications define a particular norm that are not necessarily comparable to each other. And like in order to prove convergence for each of those, we need to analyze each of them separately. The question is, can we define canonical measures so that if we achieve convergence within those measures, then we have achieved convergence within like other applications? And approximate unitary T designs have been defined exactly for this purpose. So basically, an approximate unitary T design is the distribution over the unitary group that has matching, approximate matching of moments up to that its first t moments approximately match to the ones from the Haar measure. You can think of it as a natural generalization of t-wise independence in the classical world, or you can think of it in operational terms that like t copies of a t design is going to be operationally indistinguishable from t copies of the Haar measure. So, for example, we can easily generate a one design like using a constant depth circuit, but a one design is not strong enough to generate all the other applications. But it turns out that the two design is strong enough to, in particular, generate the list of applications that I've mentioned here. So let me talk a little bit about the application of anti-concentration, which is, I believe, is the main application of this paper, this work. So as I said, collision probability encodes the concentration properties of the output distribution of the unitary circuit. And it is according to this definition. So if we can show that in expectation value, the distribution of unitaries that we pick according to, let's say, the random circuits of a certain depth, if it happens that in expectation value we get some constant factor divided by 2 to the n, then assuming certain conjectures, we will get that sampling within total variation distance from the output of a quantum circuit within that certain depth is going to be hard for a classical computer. And the conjectures are one from complexity theory that polynomial hierarchy is infinite, and that certain counting problems are hard to approximate on average, and these counting problems are related to the amplitudes of the quantum circuit that a random quantum circuit in particular. And this is related to a recent proposal by the Google Quantum AI group that has proposed to implement this random circuit sampling model, that the model basically being that like we apply a random circuit of certain depth on all zeros states, and then we sample a string of bits from this, and like using classical computer science, we want to show that these distributions should be hard to sample for a classical computer. And what they needed in this work is that like we want to say that like circuits with shortest possible depth satisfy this property. So to just give you an overview of like what we know about anti-concentration, at depth 0, this expectation value is just going to have collision probability 1. So it's very large, exponentially large compared to 1 over 2 to the n. And when I converge to the Haar measure, then I'm going to have in expectation 2 over 2 to the n plus 1. So now the question is, as I run the circuit, how fast do I converge to this small value? So basically, the question that is needed for these experiments that Google is interested to build is for d equals 2, for circuits applied to qubits on a square grid. And so from previous work of Haar and Loh and Brandau, Haar and Hordetsky from 2010 and 2012, we know that for the architecture of a complete graph, a random circuit that we can apply random gates between any pair of qubits, and a one-dimensional chain, linear depth is enough in order to achieve anti-concentration. Well, they achieve conversions in stronger norms, namely T designs, or this work just achieves 2 design, which implies anti-concentration. And prior to this work, nothing was known better than linear depth for any circuit architecture. And basically, for a random circuit on a 2-dimensional lattice, it was conjectured by the Google group that like a square root of n depth is enough for achieving the anti-concentration property. And that is basically what's motivated this work. And we confirmed that for the particular type of circuits that we consider, this conjecture is correct. Okay, so now I'm going to briefly talk about the results. So, as I said, the models that I consider correspond to like lattices, in particular one-dimensional lattice. And I separate the one-dimensional case and cases with dimension greater than or equal to 2, or random circuits with long-range gates. And this column specifies the depth required to achieve the measure of convergence. That the last column is the measure of convergence that I'm interested in. For the first two models, I'm interested in T designs, and for the last one, we only studied the anti-concentration measure, which is basically weaker than 2 designs. And I consider T to be a constant because this work only improves on the bounds that depend on n, the number of qubits. So these are all the previous bounds that we know, that we know before this work. So for the lower bounds, basically we know these numbers, but what is relevant is that the diameter of the graph is basically, so each of these numbers are just the diameter of these graphs. And it's not hard to see that in order to achieve each of these measures, you need at least the number of gates equal to the number of the diameter of the graph in order to achieve each of these measures. So to just give you a picture, for example, consider a perturbation initialized at the beginning, and then I need to apply overlapping gates, at least as many as the longest path in the graph in order to for this perturbation to propagate throughout the circuit. Otherwise, the information, intuitively, the information has not mixed enough between the qubits. Okay, so for the upper bounds, the best bounds that we knew for achieving these norms were linear depth. So for T designs, for one-dimensional grids, the work of Brandau, Haar, and Hordetsky from 2012 shows that order n linear depth is enough to get T designs. And for anti-concentration, as I mentioned, the result of Haar and Low achieves 2 designs, which implies anti-concentration. And nothing better than linear depth was known for either of these circuit architectures. So our first result is that we improved this lower bound to log n. So even though the diameter of this graph is a constant, we need at least log n many qubits in order to converge in the anti-concentration measure. And we furthermore show that this bound is matching up to log n factors. So essentially, log n is the bound that we need. And for the 2-dimensional, 3-dimensional, and so on, d-dimensional cases, we confirm that the diameter is actually the right depth bound in order to achieve T designs. Okay. So now I'm going to be more specific about the definitions and the results that we achieve. And I'm going to talk about the proof techniques that we used for this work. Okay, so let's just start off with the definition of the moments. So as I said, the definition of T designs is according to moments of a unitary match between 2 distributions. So by moments, in particular, we're interested in balanced moments. So we start with the balanced monomial, which is basically T copies of the unitary U and T copies of the complex conjugate. And each of these indices, I1 through IL, is running through the all set of bit strings that is possible. So it's basically T copies of the entries of U and T copies of the entries of U star. And a moment is basically the expectation value of this monomial according to the distribution that we're interested in. So now a T design is basically a distribution such that each of its moments or each of its balanced moments is approximately matched with the ones from the Haar measure. Uh, just to specify, like we're only interested in balanced moments because the ones that are not balanced are going to have zero value according to the Haar measure, and it's they quickly get killed off for any reasonable circuit model. So now the thing is that we have exponentially many elements to figure out. Like if you want to define the convergence, so it would be interesting if we can encode all of these numbers in a single matrix. And basically we define a matrix that we call quasi-projector for the reason that I'm going to explain in a moment, that encodes all of these moments as its entries. So the matrix G contains T copies of the unitary U and tensor product, tensor T copies of U star. And we take the expectation value, so it's a gigantic matrix, with the property that each of its entries is going to be one of the moments of the measure. And we call this a quasi-projector because it turns out that if we happen to have mu to be to the Haar measure, then this operator would be a projector. And as we increase the size of the circuit, we get closer and closer to a projector. So because of that, we call this operator a quasi-projector. So because I have a matrix, now I want to, so basically the definition of a T design is just a way of comparing the quasi-projector corresponding to a distribution mu with a quasi-projector corresponding to a distribution according to Haar, the Haar distribution. And since these are matrices, we inevitably have to define the convergence according to the difference between the closeness of these two operators in some norm. So this norm can be a one norm, infinity norm, and so on. Or we can define measures according to applications, for example, decoupling, scrambling, and anti-concentration, which we considered in this work. And the last piece is that the particular model that we consider has a certain structure in it. So it has two steps, which we call column mix and row mix. So in the column mix, I basically shuttle back and forth between two ways of applying gates on the rows of on the columns of the matrix, and I continue for around the square root of n rounds, times some polynomial in T. And the row mix is the same thing applied to rows. And again, it is continued for a square root of n rounds. And both of these processes are repeated for some polynomial in T number of rounds. And for d greater than 2, there is going to be a little bit more complicated structure in the circuit. So now I'm going to, given this definition, I'm going to sketch the proofs of the theorems. So let me briefly mention what the theorem you're going to prove, or I'm going to sketch the proof for. So basically, this is the result for d-dimensional lattices. And we show that we achieve approximate T designs after the diameter of these, after depth equal to the diameter of these circuits, times some polynomial in T, in a variety of measures. So basically, one measure is that each of the moments separately matches the one from the Haar measure, or we have other norms that are well known in this field, like diamond norm, trace norm, or infinity norm. And also, we construct the convergence in diameter for other norms corresponding to applications of anti-concentration, decoupling, and scrambling. So I should note that for the last two elements, scrambling and decoupling, we only save logarithmic factors from the previous results of Brown and Fuzzy. But for neither of the previous ones, we didn't know anything better than linear depth. OK, so now let me start off by saying, like, what is the issue? Why do we always get linear depth? So I'm going to explain the situation with the work of Brandau, Haar, and Hordetsky. So basically, the projector corresponding to the Haar measure is going to project onto a t factorial dimensional subspace. So if I consider the sort of list of singular values, it's going to have t factorial 1s, and the rest are going to be zeros. And what Brandao, Haar, and Hordetsky show was that after a circuit of certain depth, the second largest singular value of this matrix is going to be damped by a value proportional to a value like e to the minus omega depth. So basically, I'm going to be a lot of small numbers here. And like I will have the t factorial 1s here. So basically, these two norms are close to these two matrices are close to each other within infinity norm, but we have a lot of non-zero terms here. So in order to, yeah. So if we, you can show that the subspace that these Haar measure projects onto corresponds to a vector space of dimension t factorial. So that they have a particular definition. So basically they are, so consider a maximally entangled state and consider the permuting the right-hand side of these maximally entangled states. So they have t copies there. So for those t factorial permutations, they define a t factorial dimensional vector space. Yeah, thanks. Okay, so now I'm going to, so now in order to get more practical norms, so infinity norm is not very practical for applications, we need to change the norm, which is basically multiplying rank by the infinity norm in the naive way. And since the rank is exponentially large, we inevitably need depth to be linear in order to get small norm within this approach. So linear depth is what we get using a naive change of norm. So now how do we resolve this? So first remember that the model that we considered first had a column mix operation, which basically shuttled back and forth between the columns. But now if you look at each of the columns as a one-dimensional system of size square root of n, using the work of Brandao, Haar, and Hordetsky, which is mixing within linear depth according to the according to the T design measure, we show that we can basically replace the operation as applying a Haar unitary in each of the columns. And the same for the rows. So the second square root of n rounds is going to be the same as applying only Haar measure on each row of the circuit. And the combination of these is going to be a cross-lamination of row and column Haar operations. So now here's the situation. Again, the projector according to the Haar is going to have t factorial 1s and zeros in the sorted list of singular values. And each of these row mix and column mix operations, which we now replace each of the elements of the circuit with, is now going to project onto some t factorial to the square root of n dimensional subspace. So we have this many 1s, and the rest are going to be zeros. And it turns out that the composition of these, again, so we show that like the second largest eigenvalue is exponentially small in the depth, which is now square root of n, but the rank is only going to be exponentially large in the square root of n. So now we don't have exponentially large rank in n. So because of this, now rank and the largest second singular value match with each other. So all norms become equivalent to each other. So there is going to be a lot of work to prove equivalence between these norms, but that is basically the main idea. So to summarize, so we first show that the composition, so we first show that the circuit that we consider is going to be basically the same as applying Haar measure on each of the rows and on each of the columns and repeating the process for a number of rounds. And the second thing that we show is that like The spectral gap is small, so basically we repeat and show the results that a spectral gap is exponentially small in the depth, which is now square root of n. And then the observation that rank and infinity norms now match allows us to transition to other norms. Okay, so that was the end of the proof sketches for the case of the d-dimensional lattices. Now I'm going to explain the situation with long-range gates, and in particular, the collision probability and the norm course that gives us the anti-concentration property that we need. So remember that what we need is that the collision probability has the value 2 over 2 to the n plus 1 times some constant, which is, this value is the one that we get from the Haar measure. So the first thing that we show is that there is some sequence of random gates that have depth log n log log n, such that this collision probability gets essentially close to the one that we expect from the Haar measure. So it's going to be within very small multiplicative factor from the Haar measure. So I should note that the circuit that we consider here has some structure in it. And so we also repeat the same argument, and we show convergence within norms corresponding to scrambling and decoupling. So just to explain how the proof works is that we get tighter analysis of the previous method that we did for d-dimensional lattices. Unfortunately, for t greater than 2, the bounds that we get is going will be exponentially large in the dimension of the lattice, and if we increase the size of the circuit is going to be very large. So we analyze using the previous method this norm and show that basically if we let d to be an arbitrary number, then after depth d times the diameter n to the power 1 over d times log d, then we get the convergence within this norm, and then we only need to let d to be log n, and then we get log n log log n bound that I showed here. But as I said, the circuit that we construct here is going to it has some structure in it. It would be great if we can define convergence for a random circuit model that we pick gates, pair of qubits at random and apply gates between them. So in a way, the sequence of gates do not have structures within them. So what we show is that after size n log n squared, then we achieve this constant factor, something like 29 divided by 2 to the n. So basically, we get the 29, some constant factor that achieves the bound that we need for hardness of sampling from a random circuit. And so since the order of gates is chosen at random, on average, the depth that we get from this circuit is going to be something like log n cubed. So basically, you can think of it as a convergence in time log n cubed. Okay, now let me explain how we achieve this bound. So the objective is to prove convergence to the Haar measure according to the norm defined according to the collision probability. So using a lot of works before this, in particular the ones from Oliveira, Dalston, and Plenio, and extensions by Harrow and Lowe and Brown and Fuzzy, we can show that the second norm in particular can be related to a certain classical Markov chain mixing problem. And since the collision probability is a certain form of the second norm, then we will get some Markov chain mixing problem in some norm corresponding to the probability distribution over the Markov chain. So now here's the Markov chain that we get. So it's going to be a birth and death Markov chain. It's going to have n number of sites. So it is reducible, but if you throw away this zero state, it's going to be irreducible. And at each step, we have some probability of staying, some probability of going left, and some probability of going right. And what is relevant within these equations is that these are second-degree polynomials according to the location on the sides, the location on this Markov chain. And what is relevant is that, so if this was a first-degree polynomial, then we could solve the model exactly. But unfortunately, this is second-degree polynomial, and we can't do that. And just to give you an idea of like how these probabilities look like, so the probability of going backwards is going to increase as I run the chain forward, as I go to the larger and larger indices. And the probability of going forward is going to first increase and then decrease. And we see that there is a bias towards getting to this region of 3/4 n, and there is on the states from the left-hand side of this chain, and a bias for getting closer to 3/4 n from right, and a large amount of wait time, like in between. So as we expect, because there is a bias from getting from left to right on the left-hand side and right to left on the right-hand side, so the final stationary distribution. Oh, sorry, the horizontal axis is the location of the, so the horizontal axis is exactly this picture, is the location of the sites of the Markov chain. And like the picture that I showed here shows the stationary probability distribution on the sites of this Markov chain. So it's going to be a binomial centered around 3/4 n. And intuitively, it's because we have bias from left to right here and right to left here. And when we translate the problem, the initial distribution on the Markov chain is going to be a binomial distribution centered around the center of the chain. And the process that we need to analyze is basically the process that this binomial distribution moves forward and slows down as it gets closer to the 3/4 n region and fluctuates when it gets here. So, but the norm that we consider here is going to be a weighted one norm. So in particular, 1/3 to the power in the index number of the state times the absolute value of the function that I compute the norm for. And the objective is that I want this norm after t number of steps to be exponentially small. And this norm is very sensitive. And the main obstacle in the analysis of this model is that, so this model was previously studied by the works of Haar and Low and Brown and Fuzzy, and they prove convergence within some other norms. And in particular, we know how to prove Markov chain mixing for this chain within one norm. But turns out that there exist perturbations that we can ignore for the one norm, that they are small. But they have large, exponentially large factors when we consider this collision norm. So this norm that we consider here. So basically, the previous bounds were not enough in order to like prove convergence for the anti-concentration application. So I'm not going to get into the details of the proof, but roughly the resolution is that we reduce the solution to this. So we have to solve the model nearly exactly. And the basic idea is that we solve the model by reducing the dynamics from what the model that we had to a well-known process known as the Ornstein-Uhlenbeck, which has applications in economics, physics, and mathematics. And the main difference is that the transition probabilities So they look very close, very much close to what we have for the original chain, but they're going to be linear. And it turns out that if you have linear dependency on these probabilities, then we can solve the model nearly exactly using a previous method of Koch from 1950s, if I'm not mistaken. And like we use that closed form solution that we get, a closed form solution that we get from that method in order to prove convergence within this norm. Yeah. Sure. Yeah. Exactly. So it's going to be so if you consider the let's say the Pauli strings of certain weight on the let's say configuration of qubits, then the location of each of these sites is going to be the weight of that Pauli string. So basically, because we have the symmetric, like because we choose any pair of qubits, then like the weight is the parameter that is relevant. Yeah. Thanks for the question. Okay, so I'm going to just explain in 1 minute what I mean by the reduction, but it's not going to be very useful. So if you're interested in, please see the paper. So basically, we condition on the Markov chain moving faster, which we call a process that we call partial acceleration. And we show that like after partial acceleration, the chain is going to be just the Ornstein-Uhlenbeck process. And the process corresponds to acceleration. So we first solve the model exactly, but then we need to reduce the answer back to the actual model that we were interested to analyze. And since we have accelerated, we need to wait for some amount of time in order to simulate the previous model. And we need to do some like wait time analysis that will require very sharp bounds. So that's basically the idea. And this is just a picture of how the Ornstein-Uhlenbeck process looks like. So basically you have a bias towards, let's say, think of this as the 3/4 n region, then like you're going to have like exponentially converge to this mean value. All right, so there are some open questions left from this work. The first one is that like there is the strongest possible norm that I didn't discuss, but in the work of Brandao, Haar, and Horodetsky, they defined that imply all the other norms that I mentioned. We couldn't achieve the convergence within that norm, and it's not even obvious if like we can achieve better than linear depth within that norm. So the second question is, can we extend this result to arbitrary graphs? On an upcoming work, an upcoming paper by Haro, Kong, Liu, and Shore, we're going to make some partial progress towards this direction that basically certain graphs that have small depth, small diameter require a lot of gates in order to get T designs based on. So basically the diameter is not the right measure after all. And are these bounds tight for anti-concentration? We have numerics that show that they should be, but we can't show them. And the constant factors can be as large as like something like 5,000, like in the constructions that we have. So they're not really useful for, let's say, near-term applications. But again, numerics or heuristics, we know that the constants should be small. And also, as I said, like we have some structure in the circuits that we have. The question is, can we prove some comparison lemma that shows convergence within one circuit architecture implies convergence within the others? And thank you for your attention. And so the references.
Do we have any questions on the matter?
Hello. Hi. Nice talk.
Thank you.
Have you given any thoughts on how to show that the random circuit sampling is hard for any T design rather than Haar random? So we have seen earlier talks that says a worst to average case hardness for random sampling. So do you have any thoughts on whether if we replace that by t-designs, what could it be? Because then you can directly apply your results by saying that you need at least something more than two design
Right.
to start doing. So do you have any thoughts on that?
So hardness of sampling is kind of uncorrelated from having a t-design distribution, because we can have like random Clifford circuits that like actually achieve like unitary two designs, which give us anti-concentration, but they are efficiently simulable. So basically, I think T design is not that does not imply hardness. And so for the random sampling model, we basically two design is enough, and actually something much weaker than that is enough. So I don't think if getting T design larger than 2 will help, unless there is another way to model this. Does that answer your question?
I'm sorry, are you saying that you wouldn't even need a two design for random circuit sampling? Is that?
So in order to get the hardness of sampling, like one direction, we need two design, and in particular anti-concentration. So larger T values for a T design is great if we have those, but it's not going to give us anything more, because we already have the bound that we need for T equals 2. Mm-hmm.
But just the anti-concentration is not sufficient to show that the output probability distribution is hard, right?
No.
Mm-hmm. Yeah, so yeah. So we should
just all Hadamars, yeah.
So
yeah.
there must be some theoretical foundation of how to use some approximated random distribution that is still hard, so that we don't need exact hard random, but some approximate.
So yeah, as I said, like these distributions basically show something about the probabilistic properties of these, and do not necessarily imply anything for the hardness. But if we have that, like for the context of random circuit sampling, it will help in constructing this hardness of sampling theorem that we need. Yeah. Thank you. Yeah.
Do we have any more questions? Aha!
What? Oh no.
So I just have minor clarification. So is it correct that your work is the first work to show that for the 2D random circuit sampling problem, that it does indeed have anti-concentration?
Yes.
That's right. Okay. Because I feel like I've been hearing this for the last couple of years, that this work has anti-concentration, and this part is the easy part. The hard part is the thing that was shown recently in the Boland et al. Paper.
So we knew only anti-concentration within linear depth only for d equals 1. And so there is no actual proof in the literature, but it is true. So there is a way to prove it by just generalizing the result of Brandau and Haar and Hordetsky, but it was never proved rigorously anywhere. Yeah.
Thanks.
Okay.
Well, just a unrelated question to that, but first a comment on that. Couldn't you just make a wiggly snake line and turn 2D into 1D and apply the same proof?
Yes, so you will achieve linear depth.
Yeah. But my other question is, when you're doing the 2D thing, you seem to do square root of n rounds of rows and the square root of n rounds of columns.
True.
And it would seem just intuitively that it would mix faster if you did one row of rounds and one row of columns, one row of rows, and so on. Is that true? Or
that is a very good question. So basically, I also have the same intuition that you apply other layers, so you're going to get even faster scrambling, but our proof techniques do not allow us to do that. So that is the comparison lemma that I mentioned in the open questions section. So that basically, if you add random gates in between your circuit, would you get faster convergence? If you can show that, then you can show convergence within any natural family of circuits. Yeah, thanks.
Are there any further questions?
In that case, let's thank the speaker again.
Thank you.